1.7. A 2 resistor voltage divider employing a 2 kilo ohm and 3 kilo ohm resistor is connected to a 5 volt ground reference power supply to provide a 2 volt voltage. Sketch the circuit. Alright, so here's a voltage divider circuit. Here's your 5 volt power supply. And the voltage divider circuit is supplying 2 volts. You can probably see if we're using 2 kilo ohm and 3 kilo ohm resistor, this would be the circuit. It's the voltage division, 2 divided by 2 plus 3s, 2 fifths times 5, 2. Cool. Okay, so assuming exact valued resistors, what output voltage and equivalent output resistance result? So that output voltage, the purpose of the voltage divider is 2 volts. And the equivalent output resistance, so the output is measured across these two terminals, right? And ground. So we want the equivalent output resistance measured across the output terminals. So the equivalent resistance seen across two terminals is the Thevenin equivalent resistance. And to find that, we short the voltage source. Okay, and then we find the resistance across the terminals of interest. So if you can bend that in your head, then you'll see that the equivalent output resistance will be 2 parallel with 3, and that's RO, or the equivalent output resistance. If you don't know how to do Thevenin equivalent, I'll have a video about it soon, and I'll put it in the link. There you go. Oh wait, there's more to this question. If the resistors used are not ideal but have a plus or minus 5% manufacturing tolerance, what are the extreme output voltages and resistances that can result? Alright, so let's set up the equation for the output voltage. VO, that's just a voltage division. So you have your 5 volt source multiplied by R2 over R1 plus R2. But these are going to have a plus or minus 5% tolerance. So this will be 2000 plus or minus 5% of 2000, and then 3000 plus or minus 5% plus 2000 plus or minus the same plus or minus 5%. So what are the extreme values? I guess we could make this big and this small, or we can make this small and this big, right? So you see what I'm saying? I don't really want to carry that out for you, but I'll do it. You know, whatever. So let's do that. Let's do what's 5% of 2000? Let's see. It's 100. And I'm guessing this one's 150. I'm confident. Hold on, I actually don't know. Yeah, it's 150. So let's do that. Let's do 2,100 divided by 3,000 minus 150 plus 2,100. 2,100 divided by that times 5. Alright, so you could get 2.12 volts. What if we subtract? So how about that? Okay. Times 5. Okay, you could also get 1.88 volts. So that's definitely the more extreme one. So it's probably the answer you're looking for. What about the resistances that could be, right? So if that's the resistance thing, so we could have 2000 plus or minus 100 times, this is the expression for the equivalent resistance with the tolerances. And I don't have it, so I'll have to do it. 2000 plus or minus 100 plus 3000 plus or minus 150. So let's see, what are the extremes? You could either add these both or subtract them both, or yeah, it makes sense to me. I feel the biggest numbers we get if we add or subtract, so let's do that. So if we add in both cases, okay, the equivalent resistance we get is 1260. Now if we subtract in both cases, okay, what's this? Okay. 1140. And I'm gonna go out here on a limb and say if you add or subtract, you'll get numbers in between there and not exactly in there. If you're curious, 2000 in parallel with 3000 gives you 1200. Exactly right in between those. There you go, you're welcome.